Due to games' rising popularity in esports, injuries relating to the eyes, neck, and hand are becoming more prevalent. The causes of said injuries are due to prolonged gaming and repetitive microtraumas. How can we, as designers, make games more injury aware? This project sought to answer that question by using a framework that gives feedback to game designers, the players, and the existence of injury-aware game AI. To test this framework, we created a tool and corresponding proof-of-concept game that tracks and exports key presses and player location. The results from the proof-of-concept game and user study showed that both players and designers had a positive reception to the idea of implementing more inclusive measures into games, with nearly all participants of the user study being interested in the idea of hand exercise recommendations. What sets our work apart from most other game-related health research is that most work was done in the fields of medicine. We instead took a designer's approach to the issues of game-related injuries. Gaming-related injuries can be broken down by their musculoskeletal hazards and issues related to prolonged gaming. For the musculoskeletal hazards, prolonged abnormal posturing can lead to neck or back pain. Repetitive microtraumas, as seen in high-intensity environments such as esports, has left over 30% of players with hand or wrist pain. Prolonged gaming sessions can lead to other health hazards such as visual straining, headaches, and potential behavioral issues, to name a few. We define injury-aware game design as a way to craft enjoyable gameplay experiences, all while informing both game designers and players about gaming-related hazards, promoting healthy gaming activities, and optimizing gameplay to avoid injury. To achieve this, one or more components must be added to the game. First, a player activity monitor to track various metrics of a player during any given session. Second, injury-aware game AI to dynamically change gameplay based on real-time player activity data. And lastly, data that can be presented to the player in relation to their session that raises awareness of gaming injuries and promotes healthy gaming activities. An injury-aware game can be based on any of the combinations of these components, as seen in this figure. The embedded player activity monitor will collect data such as keystrokes, mouse clicks, and other inputs based on a player's current controller throughout the game session. This can be used to monitor the risk of musculoskeletal hazards associated with repetitive microtraumas, as well as estimate the risk of prolonged gaming. Since most common engines have event systems and input loggers for user profiling and performance optimization, developers can expand either the engine or their own APIs to make it easier to monitor player input activities. In conjunction with the player activity monitor, a data analyzer can be embedded to analyze a player's input data and generate personalized health warnings or recommendations based on the guidelines from the medical professionals. For game designers, feedback will include an in-game UI that can be displayed and that shows a low-level, granular data gathered so that the designers can design or redesign an aspect of the game as necessary. 3 types of data can be presented: spatial, temporal, or integrated. Spatial data will be showing the player's input activities by regions of the game world, with this info potentially helping designers redesign a level to reduce the player's hand workload for said regions. Temporal information may include the intensity of player input activities over time, so that designers may redesign the game to reduce the intensity of repetitive hand activities. Pictured is the temporal aspect of the tool in the Unity engine. The integration between spatial and temporal data combines both to provide a more detailed picture. The data can be visualized through techniques such as heat maps to display both the temporal and spatial aspects. Between retooling a game or level to not over-rely on any given finger, or to better distribute interactions across a level, some genres and mechanics are inherently more stressful than others. The feedback will allow designers to review the data and decide on the best course of action to remedy the intrinsic strains of said genres or mechanics. For players, and in the case of young children, their guardians, the feedback presented is much less detailed than what would be presented to a designer. For players, three types of data are presented: aggregated player activity, as pictured, warnings about potential health hazards, and health recommendations based on the analysis of the player activity monitor. The information can be displayed either during or after a given game session, with some warnings being displayed if the gaming activities are deemed excessive based on health guidelines. The purpose is to make a player more aware of potential health hazards based on a player's personal and immediate gameplay data. Players, in turn, will feel the info is more relevant because it is delivered in-game, in real time, and is based on their own personal data. For younger children, info may be delivered separately as a report to either the parents or guardians to keep them informed, providing more specific information about hand activity, warnings, and health recommendations. Injury-aware game AI can be used to dynamically adjust gameplay in real time in order to reduce the risk of injury or prolonged gaming. The AI takes inputs and statistics from the player activity monitor and compares them to a health info database. If the player's activity goes outside normal ranges, as defined by health guidelines, the AI can adjust the gameplay as necessary. Injury-aware game AI is technically feasible, as numerous games feature adaptive gameplay such as dynamic difficulty adjustments. The difference here being to now incorporate gaming health guidelines into said algorithms. The proof of concept game is based on Katamari Damacy, where players roll a ball around a level to pick up items. The game consists of one level, split into 9 zones, where players roll a ball around to pick up items according to unlocked categories, shown by the highlighting of the items. The win condition is to have a ball of about 2.5 meters, which on average took players about 9 minutes to complete. We did not develop an injury-aware game AI for this proof of concept. We created 2 separate versions: the experimental group, the injury-aware version, which switches the controls from WASD to the arrow keys every 30 seconds. The experimental group is denoted by having a radial in the top right corner indicating which controls to use at the given time. And the control group, which allows players to use either WASD or the arrow keys at any given point. The experimental group version allows for a break on the player's hand for that given duration. Pauses and breaks in a game are set in motion by players or an event happening in-game. These serve as natural checkpoints for players to catch up and reflect on what's going on in the game. For injury-aware gameplay to work while still being enjoyable, it needs to balance the subtlety of breaks without interrupting the game flow too much. Our player activity monitor features 2 components: a temporal aspect in the form of a keylogger, and a spatial aspect in the form of an area or zone ID. The keylogger records both WASD and arrow keys at every instance in time, no matter the version. The counts will be averaged over a period of time, in the case of this game, over a period of 10 seconds. Because our game only had one level that took around 9 minutes on average to reach the win condition, we decided to set a short time span to continually export our data. The spatial aspect is game and mechanics specific, but in our case is meant to track the player's location. In the proof of concept game, the level is split into 9 areas, with each item being tagged with a zone ID. If the player picked up an item, it would be added to the respective zone's overall count, showing where the player was within the last 10 seconds. The spatial component, or the zoning tool, can be used in a variety of contexts and manners outside of this proof of concept. For an open world game, the zones can be split, say, by the LOD chunks on a given terrain, with each object to be tracked based on a zone ID. Another example would be a rhythm game. Most beat maps are already sectioned off into parts, so each note in said part would be tagged to the zone ID. The 2 aspects work in conjunction to give an idea of how the players are using their fingers over a period of time in relation to how objects are distributed throughout a level. Game designers will be able to view the raw data in the Google Sheets, port the data into a data visualizer, and view both hand usage via the keylogger as well as players' movement and interactions throughout a level via the zoning component. Heat maps display the density of finger usage to standard keyboard finger configurations. Once a session ends, or a designer feels as though enough data has been gathered, they can use their visualizer of choice to view the overall impact of the player's finger usage and location by creating a heat map. In our game, we use Plotly, but again, designers are free to use whatever data visualizer they choose. Designers can view these heat maps to show both the density of finger usage as well as if there's any correlation of object interaction or inaction between two heat maps. Levels in any given game could potentially be redesigned accordingly if certain fingers are overused. Players and their guardians do not need to see the raw, unaggregated data, but rather a condensed summary based on the data gathered throughout the session. They can receive a bar chart based on the sum counts of each inputs. On these aggregated counts, a recommended hand exercise will be provided. If followed up on by the players, these recommendations can also aid to preventative measures against developing any gaming-related injuries. As stated earlier, we did not develop injury-aware game AI in our proof-of-concept game. In our game, the AI would not serve much purpose other than to potentially force a break if the player's inputs go outside the quote-unquote healthy range. In other contexts, say a rhythm game, a counter for the number of retries can run in the background, and after a certain threshold is reached, offer to automatically lower the difficulty of the current beat map. Another example being input-based fighting games, which have repetitive strains due to how much a player will be responding to an enemy's moves. In this case, a counter tagged by the moves that damage the player can be implemented. Based on the moves that hold the highest count, indicating which moves the player is struggling with the most, the probability of said moves being used by the computer can be reduced in subsequent replays of the current round or session. Between the two studies, we gathered 29 people, 19 who played the game prior and consented to having their game session recorded, and 10 who participated solely in the user study questionnaire, with 60% of those who participated identifying as game designers or developers. All participants were interested in the idea of receiving hand exercise recommendations after play, with the majority of the designers finding both aspects of the tool beneficial for any given project. Gaming injuries have become an important health issue as a large portion of the population plays video games regularly, and the popularity of esports is growing rapidly. We believe an effective way of delivering gaming-related health information to players is to embed the info in the game's design itself. The results showed that participants, both players and designers, would be open to exploring the avenue of injury-aware gaming, with the most positive reception of the feedback being recommendations for hand exercises. User study participants who played in the injury-aware version of the game did not find their enjoyability hindered by the control switching mechanic, and designers felt both the temporal and spatial aspects of the tool to be beneficial to level design. This work is the first step towards a comprehensive study of injury-aware game design, with many research questions remaining to be studied. We look forward to a more inclusive and injury-aware future in gaming.